Layered deposits blanket the floor of Tuskegee Crater. These sediments may have settled in an ancient lake. Different colors reveal distinct layers across the crater floor. Patterned ground marks the surface in striking formations. These patterns likely formed as muddy sediments dried and shrank over time. The variations hint at cyclic deposition events. Each layer preserves a snapshot of ancient Martian climate. The colors suggest changing mineral compositions during formation. This crater floor holds clues to when liquid water pooled on Mars. The layering remains remarkably intact after billions of years. Alluvial fans spread across Saheki Crater in gently sloping wedges. Flowing water deposited these sediments long ago. Saheki preserves some of the best alluvial fans on Mars. Two impact craters slice through the fan deposits. These craters expose the internal stratigraphy like a natural cross-section. Each layer records a separate flood event. The fans built up over countless water flows. The stratigraphy reveals the sequence of ancient flooding. Studying these exposures helps decode when water shaped this terrain. The preservation here surpasses most other Martian fans. Contrasting surfaces divide this small crater in Hellas Montes. One side displays a smooth scarp. The other side shows a gentle slope with rough texture. Is the crater emerging from burial or sinking into sediment? Orientation may control how these surfaces develop. The smooth scarp faces one direction consistently. The rough slope faces the opposite way. This asymmetry suggests directional processes at work. Wind or ice could sculpt each side differently. Understanding these surfaces reveals how craters age on Mars. The contrast between sides provides critical clues about erosion patterns. Rocky fill rises in higher relief across eastern Romer Crater. This ancient impact basin spans 120 kilometers in Noaches Terra. The crater honors University of Arizona astronomer Elizabeth Romer, who lived from 1929 to 2016. The rocky material accumulated long after impact. Subsequent processes deposited or exposed this fill. The eastern section shows particularly prominent rocky textures. These materials may record later geological activity. The fill contrasts with smoother crater floor elsewhere. Studying this distribution helps reconstruct the crater's evolution. Romer Crater preserves a complex geological history in its interior. An ancient meandering river carves through the Zephyria region in raised relief. Inverted topography marks where the channel once flowed. Cemented riverbed sediments resisted erosion over time. Surrounding floodplain materials eroded away, leaving the channel elevated. Yardangs align north to south across the landscape. Wind scoured and carved these ridges like landforms from bedrock. The main channel stretches about 13 kilometers. Elevation drops 113 meters from north to south based on altimeter data. Increasing sinuosity downstream suggests flow toward the south-southwest. The preserved meanders reveal how water once sculpted this terrain. Layered rocks stack across Ophir Mensa in distinct formations. An unconformity cuts through the sequence. This break in time interrupts an otherwise continuous rock record. Above and below the unconformity lie rocks of different ages. The contact between them marks a gap in deposition or erosion. Structural measurements help interpret the geological history. A digital terrain model aids future mapping efforts. The layers preserve multiple episodes of deposition. Understanding this unconformity reveals when processes paused or changed. The rocks record a complex sequence of events on ancient Mars. A channel carved within a larger channel cuts through terrain near Hellas. Did flowing water or lava create this nested structure? Both fluids erode and sculpt channels. Water carves through rock. Lava both melts and erodes its surroundings. Perhaps a surge formed the wide channel, then subsided to a trickle. Or maybe a trickle carved the inner path before a later surge widened it. The channels lack raised levees along their edges. The inner channel diverts around a central mound that once stood as an island. Analyzing the shapes could reveal which fluid flowed here and in what sequence. A light-toned deposit sprawls across chaotic terrain in Orium chaos. Layers appear within the deposit. Shapes suggest a fluid moved north and south, eroding the material. The deposit's top surface appears rough and textured. This roughness contrasts sharply with surrounding smooth plains. The light tone indicates different mineral composition or grain size. Chaotic terrain forms when ground collapses, removing support from below. This deposit may have filled depressions after collapse occurred. Or perhaps the deposit existed first and chaos formed around it. The layering records multiple deposition events in this disrupted landscape. A collapse pit opens in the south polar layered deposits. The rim casts shadow, confirming this feature descends rather than rises. Sunlight direction reveals which side should darken. The pit formed as material underneath gave way. Why did collapse occur in this location? The layered deposits contain ice and dust in alternating bands. Perhaps ice sublimated, removing support for overlying layers. Or maybe a void existed below, waiting to trigger failure. The circular shape suggests collapse happened rapidly. Understanding why this pit formed reveals processes active at the Martian poles today. Multiple mantle layers drape across Icaria fossae. Sedimentary features extend to the north of the layers. Crater infilling appears to the south. No previous high-resolution images covered this area. The mantle layers blanket underlying terrain. These deposits may record atmospheric dust settling over time. The sedimentary features suggest fluid or wind transport. Craters to the south filled with later material. This combination makes the region valuable for geologic mapping. Each feature type records different processes. Together they reveal how this landscape evolved through Martian history. Ridges and depressions carve through Lycosulci, northwest of Olympus Mons. Thick Martian dust blankets this landscape in light tones. Dark streaks slice down slopes when dust suddenly slides. These streaks expose darker volcanic surfaces beneath. Fresh streaks appear dark, then lighten as atmospheric dust settles again. Two ridges reveal partially exposed bedrock still coated in dust. The ridges likely formed through volcanic and tectonic forces. Wind erosion and mass wasting sculpted them further. Talus slopes fan out from the steepest portions. Rock and sediment fail under Martian gravity, triggering avalanches. The materials accumulate downslope in conical deposits. Sedimentary deposits fill portions of Eos chasma. Most large chasmata in Valles Marineris contain kilometer-thick sulfate layers. Eos chasma either lacks these deposits or holds much thinner accumulations. Light-tone materials appear along the floor and inner walls. Some deposits formed after the chasma floor developed. Other deposits lie beneath wall rock materials, indicating greater age. The stratigraphy reveals multiple episodes of deposition. Understanding their sequence helps reconstruct the canyon's history. The variation across chasmata suggests different formation processes. Eos chasma preserves a distinct sedimentary record compared to neighboring canyons. Geological contacts intersect near Cugun Valles, close to the Oxia Planum site. The ExoMars 2020 mission targeted this region for landing. Multiple features overlap, revealing their formation sequence. Impact craters puncture the terrain. Lava flows buried earlier surfaces. Wrinkle ridges deform the landscape. Crossing these contacts determines the order of events. Each feature records a distinct geological episode. Understanding the stratigraphy reconstructs how this area evolved. The relative ages clarify which processes occurred first. This sequence matters for interpreting Martian geological history near the landing site. Alluvial fans merge to form bajadas across this section of Coprates chasma. Water once deposited these fan-shaped sediments. The fans appear related to light-tone deposits at the canyon base. Fans spread from both north and south walls. Their relationship with floor deposits reveals flooding history. Possible normal faults cut through the fan sediments. These faults help determine timing between faulting and sedimentation. Understanding this relationship clarifies how Valles Marineris evolved. The fans preserve evidence of water flowing into the canyon. Studying their structure decodes ancient hydraulic processes in this massive canyon system. Seasonal frost coats gully alcoves in a crater on the northern plains. Carbon dioxide frost dominates at middle and high latitudes on Mars. This dry ice differs from water ice frost. Frost accumulates differently based on slopes, shadows, and material type. Rugged rock outcrops appear dark and shadowed. Frost highlights the upper alcove and steepest downslope routes. Most gully changes occur in the southern hemisphere. Northern hemisphere steep slopes are less common. Monitoring reveals frost behavior and potential surface activity. The frost may trigger flows in gullies. Understanding these processes clarifies how seasonal cycles shape Martian terrain today. Dark dunes march across fractured bedrock, leaving gaps between. The substrate resists wind erosion, revealing its solid nature. Fractures shatter the surface from bending stresses or temperature changes. Cooling could crack bedrock in such patterns. Alternatively, sedimentary layers may have shrunk and fractured while drying. These would form like gigantic mud cracks. Dark sand grains trap within the relatively small fractures. The trapped sand makes fractures quite distinct now. Examining orientation and spacing reveals formation processes. The fractures pattern the ground beneath mobile dunes. This resistant surface preserves a record of ancient stresses or environmental shifts. A circular depression cuts into dark-toned terrain northeast of a cone field. Layers appear along the depression walls. Dark sands blanket these layers. The sands associate with the surrounding dark-toned unit. Higher resolution imaging reveals the layered structure more clearly. The layers record successive deposition events. Dark material drapes over the exposed stratigraphy. Understanding these layers helps decode the region's geological history. The depression exposes what lies beneath the dark unit. Analyzing the layering sequence reveals how this terrain accumulated over time. The relationship between layers and overlying sands clarifies depositional processes. This plateau region of Ares Vallis contributed little to overall water discharge. The main channel lies downslope at the northeast edge. Transverse aeolian ridges now cover channel bottoms. These dune and ripple-like features formed from wind. The ridges orient perpendicular to wind, flow through the dry channels. Tars reveal current wind patterns in these ancient waterways. Water once carved these channels. Wind shapes them now. The ridges march across the channel floor in parallel lines. Their orientation records persistent wind direction. Understanding tar formation clarifies how aeolian processes rework fluvial landscapes on Mars. Golden crater floor displays inverted channels and rounded lobe-like landforms. Light-toned layered deposits line the southern crater wall. The inverted channels suggest former water flow. Cemented channel sediments resisted erosion better than surroundings. Erosion removed weaker materials, leaving channels in raised relief. The rounded lobes may indicate flow or collapse processes. Layered deposits along the wall record multiple deposition events. Each layer preserves distinct conditions during formation. The combination of features suggests complex geological history. Water likely played a role in shaping this crater interior. Studying these landforms reveals how fluids and sediments interacted here.